So before proceeding with differential equations, let us recall, for example, why. How do we know that this function satisfies the following differential equation? And one of the ways, maybe the simplest one to see this, is to use the series representation of the exponential. So in particular, let us calculate the derivative of this series. Term-by-term differentiation gives the following. So derivative of the first term is just 0. Second, derivative of the second one gives unity. Then x squared over 2 differentiated gives x, etc. And in fact, you may convince yourself that all of these terms differentiated will just reproduce the original series. So, and this simple exercise is generalizable to Kummer's function. And again, let us recall the basic definition. It will appear from slide to slide so that you can memorize it. And in a very similar manner, we may calculate first and second derivative of this function over x. And in fact, our goal for now will be to establish the following differential equation. And our general strategy will be the same as we kept in the previous example. So in order to check this, we need to calculate first and second derivative, keep them in the form of a series, and then substitute back to the differential equation. And then, by construction of this procedure, in the left-hand side, we will get a certain series in non-negative powers of x. And we must convince ourselves that all terms of this kind identically vanish. So how to do this? Let us, for example, check that a term proportional to x in the first power in this equation, after this series is substituted, does indeed vanish. So let us check, first of all, how do we obtain in this left-hand side terms which are proportional to x to the first power. So in order to get it, from the second derivative, we must extract terms proportional to x to the zero power. In other words, terms proportional to constant. Here, both x to 0 power and x to first power will contribute, as the prefactor has both x-independent and x-dependent parts. And finally, from this term, we have to extract x to the first power. And after all this is combined, let us see what do we obtain. So from the first term, we get this sign plus the following contribution. It is just nothing but a second derivative of this function at x equals 0, and it is determined by this term. Next, let us see what comes from this term. Now let us turn to the second term. Again, it comes with sign plus, and from b we have the following contribution. It comes again from the third term in this definition. So this contribution comes from term proportional to b, and this contribution comes from term proportional to x. And finally, the last contribution comes from sign minus, from the third term in the differential equation, and it becomes, again, we need to extract the term proportional to x in our function. So combining all this together, let us see what we have. And finally, what we need to check is what does the sum equal to. Gathering all the terms together, And now it's time to check what do we have in the numerator. So let's now count all the cancellations. So this term cancels with this one. Next, this A cancels with this one. Next is that this BA cancels with this one. And finally, all that we are left with is BA squared here and BA squared here. And they cancel each other. So indeed, this term is identically 0. So in fact, this exercise can be done in more general form when you just count the powers in front of arbitrary power of x. And you can easily show as your homework exercise that each of these coefficients vanishes. And this fact actually proves that this function given by the convergence series does indeed solve this so-called Kummer equation. In our next module, we will discuss how to obtain another linearly independent solution of this second-order equation.